Well, hey physics folks, welcome to Doc Onco Physics. Keith Onco here. Today what we're going to be looking at is another problem that has to do with an electric charge in an electric field. And the problem that we have today is that we have a negative charge. Whoops, let's go to pencil mode there. We have a negative charge which is in a position where it's most happy. It's right next to the positive plate, and so it's just going to sit there. Okay, but what we're going to do is we're going to take and we're going to do some work on our negative charge by moving it all the way down to the negative plate. We have to do work on it because the negative charge does not want to be near other negative charges, right? It's kind of like one north end of a magnet next to another north end of a magnet. It takes force in order to do that. So it takes a force, or it takes work, to move this negative charge way up at the top down to the bottom negatively charged plate. So the situation that we have here is that we have a plate that is 8 millimeters from one side to another. And we have a negative charge Q that is equal to negative 3.5 times 10 to the minus 6th coulombs. Okay, and it happens to have a mass of 3 times 10 to the minus 6 kilograms. Okay, so those are the things that we know so far. Now, it's going to take 70 joules of work in order to move this negative charge all the way down to the negative plate right down here. So the work that we're going to do is going to be 70 joules of work, or 70 joules of energy is going to be imparted into this negative charge, which is quite a bit of energy for a relatively small charge. Okay, so the first thing that we'd like to know is what the electric field must be in order for us to move, or in order for it to take 70 joules of energy to move the charge from one plate to the other plate. So we're looking for the electric field value. Okay, we don't know that. Well, what are some of the things that we do know? What are some of the equations or tools that we can use to do this? Well, we know that work, in an electrical sense, divided by a test charge is equal to some potential difference, or voltage. Okay. We also know that voltage is equal to an electric field value times the distance between two plates. Well, we know the distance between the two plates is 8 millimeters. Okay. We know the value of the electric charge, right? And we know the work that was done on it. So we also have, we can rearrange this equation to say that work is equal to Q times E times D. Okay. And now we can simply plug in the values and figure out what the electric field is. So the work is 70 joules. Right, and that's equal to negative, we don't need a Java update once again, so let's get rid of that. Negative 3.5 times 10 to the minus 6th coulombs, times E, which is what we're looking for, times D, which is 8 millimeters, or 0.008 meters. Okay, so this is the equation that we need to solve. We simply divide each side by the charge on the charge and the distance between the plates, and we get a value for the electric field that is equal to negative 2.5 times 10 to the 9th newtons per coulomb. And the negative sign just indicates the positioning of the positive and the negative plates. Okay, so that's how we find the electric field. Okay, just scroll down here a little bit. Next, what we'd like to know is we'd like to know the speed of the charge. If once we move the charge all the way down here, so the charge is moved all the way down here, we've given it that 70 joules of energy, and we happen to be able to let it go, what's going to happen is it's going to go right back up where it started from, right? Because it wants to be repelled from the negative part of the electric field, and it wants to go to the positive part of the electric field. And so it's going to move. What's going to be the velocity just before it hits that, that positively charged plate? Well, how much work did we put into that electric charge? We put 70 joules of energy into it. Okay, that's the potential energy that we gave to that charge. What's going to happen to all of that energy? Well, as it moves up here, it's going to lose that potential energy and gain kinetic energy. And by the time it just about gets to that positive plate, all of that potential energy will now have turned into kinetic energy. So 70 joules is going to be 1/2 mv squared, all right? Which means that 70 joules is going to equal 0.5 times the mass of the charge itself, which is 3 times 10 to the minus 6 kilograms, all right, times v squared, all right, and what we're looking for is v. And we do the math here, we find out that v is equal to 6,831 meters per second. So it's moving at a pretty good clip. Okay, so that's how we find the velocity. It's really based on the energy that we put into it. The last thing that we would like to do here is we would like to know the potential difference between the two plates. Well, let me just scroll back up a little bit here. The equation that I have over on the left-hand side, all right, work divided by Q equals V, which equals ED. Well, we now know E, right? E is negative 2.5 times 10 to the 9th newtons per coulomb. D is 8 millimeters. So to get the potential difference between the plates, V is just going to be E times D. So negative 2.5 times 10 to the 9th newtons per coulomb times 0.008 meters, right? And that gives us a voltage of 2 times 10 to the 7th volts. So pretty big potential difference. Okay, so that's how we analyze work and energy in a charge in an electric field. Hope that helps, and we'll see you next time.